Docker is one of those technologies that quietly reshaped how modern software is built, shipped, and run. Yet many people still hear the word and think it's either extremely complicated or only meant for big tech companies. To truly understand what Docker is, it helps to step back and look at the problem it was created to solve. For decades, developers have struggled with an issue that sounds simple but causes endless frustration. Software works perfectly on one machine but fails miserably on another. A developer writes an application on their laptop, tests it, and everything runs smoothly. Then the same code is sent to a tester, a colleague, or a production server, and suddenly it breaks. Different operating systems, different library versions, missing dependencies, conflicting software, and environment differences, all combined to create what became known as "it works on my machine" syndrome. Docker was designed to eliminate that problem by creating a consistent, portable, and predictable environment for applications, no matter where they are run. At its core, Docker is a platform that allows you to package an application together with everything it needs to run into a single unit called a container. This includes the application code, runtime system libraries, dependencies, and configuration. Once packaged, that container can be run on any system that has Docker installed, whether it's a developer's laptop, a company server, a cloud platform, or even a tiny virtual machine. The promise is simple but powerful. If it runs in Docker here, it will run the same way everywhere else. This consistency is what made Docker so popular so quickly across the software industry. To understand Docker properly, it's important to understand what containers are and how they differ from traditional virtual machines. Before Docker, virtualization was the main solution for isolating applications. A virtual machine emulates an entire computer, including its own operating system, on top of another system. Each virtual machine has its own kernel, system services, and resources, which makes them relatively heavy. They consume a lot of disk space, take time to boot, and require significant memory and CPU overhead. Containers, on the other hand, share the host system's operating system kernel while keeping applications isolated from each other. This makes containers lightweight, fast, and efficient. A container can start in seconds or even milliseconds, compared to minutes for a traditional virtual machine. Docker didn't invent containers from scratch. Container technology had existed in Linux for years through features like namespace and control groups. What Docker did was make containers accessible, standardized, and easy to use. It provided simple tools, clear workflows, and a consistent format that developers could rely on. Docker turned containerization from a niche, low-level system concept into a mainstream development and deployment tool. This ease of use is a major reason Docker became so widely adopted. When you work with Docker, everything starts with an image. A Docker image is a blueprint for a container. It is a read-only template that defines what goes inside the container, including the base operating system layer, installed software, libraries, environment variables, and the application itself. Images are built using a file called a Dockerfile, which contains step-by-step instructions written in plain text. Each instruction in a Dockerfile creates a new layer in the image. These layers are cached and reused, which makes Docker builds faster and more efficient. If only one part of the image changes, Docker doesn't rebuild everything from scratch, saving time and resources. Once an image is built, it can be turned into a running container. A container is essentially a live instance of an image. You can think of an image as a recipe and a container as the dish that's actually been cooked. You can start, stop, pause, restart, and delete containers as needed. Containers are isolated from each other and from the host system, which improves security and stability. If one container crashes, it doesn't necessarily affect others. This isolation makes Docker especially useful for running multiple applications or services on the same machine without conflicts. One of the most powerful ideas behind Docker is immutability. Instead of modifying running systems manually, you build new images when changes are needed and deploy new containers from those images. This approach encourages reproducibility and reduces configuration drift, which is the gradual divergence of systems over time due to manual changes. With Docker, your infrastructure and application setup are defined in code, making them easier to version, review, and reproduce. This aligns closely with modern DevOps practices and the concept of infrastructure as code. Docker also includes a system for storing and sharing images called a registry. The most popular public registry is Docker Hub, where developers can upload and download images. Docker Hub hosts thousands of official and community-maintained images for popular programming languages, databases, web servers, and tools. Instead of setting everything up from scratch, you can start from an existing image and build on top of it. For example, If you're developing a Python application, you can start with an official Python image that already includes the correct runtime and basic tools. Organizations can also run private registries to store internal images securely. Another important part of Docker is networking. Docker provides built-in networking features that allow containers to communicate with each other and with the outside world. Containers can be connected to different types of networks, such as bridge networks, host networks, or overlay networks. This makes it easy to create multi-container applications where different services work together. For example, a web application might consist of one container for the front end, one for the back-end API, and another for the database. Docker's networking tools allow these containers to discover and talk to each other using simple names instead of hard-coded IP addresses. Storage is another key consideration when working with containers. Containers are designed to be ephemeral, meaning they can be created and destroyed by default. Any data stored inside a container is lost when the container is removed. To handle persistent data, Docker provides volumes and bind mounts. Volumes are managed by Docker and stored outside the container's file system, making them ideal for databases and other stateful applications. Bind mounts allow you to map directories from the host system into the container, which is useful during development when you want changes in your code to be reflected immediately inside the container. Docker is often associated with microservices, a software architecture style where applications are broken into smaller, independent services that communicate over a network. Containers are a natural fit for microservices because they allow each service to be packaged and deployed independently, with its own dependencies and configuration. This independence makes systems more scalable and flexible, but it also introduces complexity in managing many containers at once. While Docker itself can run containers, managing large numbers of them usually requires orchestration tools. This is where Docker's role in the broader container ecosystem becomes clear. Docker focuses on building, packaging, and running containers. But for large-scale deployments, tools like Kubernetes are commonly used to orchestrate containers across clusters of machines. Kubernetes handles tasks such as scheduling containers, scaling applications, managing failures, and rolling out updates. While Docker and Kubernetes are often mentioned together, they solve different problems and complement each other. Docker creates containers. Orchestration platforms manage them at scale. From a developer's perspective, Docker dramatically simplifies the development workflow. Instead of installing and configuring complex software stacks directly on their machine, developers can run everything in containers. This keeps the host system clean and avoids dependency conflicts. New team members can get started quickly by pulling the same Docker images used by the rest of the team. Continuous integration and continuous deployment pipelines also benefit from Docker because tests and builds run in consistent environments, reducing unexpected failures. Docker is not limited to web applications or cloud services. It can be used for almost any type of software, including command-line tools, desktop applications, data processing pipelines, machine learning workloads, and more. Because containers are lightweight and portable, they are also popular in edge computing and Internet of Things scenarios. Developers can package applications once and deploy them across a wide range of devices and environments. Security is another area where Docker provides both benefits and challenges. Containers isolate applications, which can reduce the attack surface compared to running everything directly on the host system. However, containers share the host kernel, so vulnerabilities at the kernel level can affect all containers. Docker includes features like user namespace, second profiles, and read-only file systems to improve security, but using Docker securely still requires best practices. This includes using trusted images, keeping images up to date, minimizing container privileges, and scanning images for vulnerabilities. Performance is often a concern for people new to Docker, but in most cases, containers perform very close to native performance because containers share the host kernel and don't emulate hardware. The overhead is minimal compared to virtual machines. For many workloads, the difference is negligible. This makes Docker suitable for performance-sensitive applications as well as development and testing. Docker has also influenced how people think about software distribution. Instead of distributing applications as installers or archives, developers can distribute Docker images. This ensures users get the exact environment the application expects for open source projects. This can reduce support issues and make it easier for users to try out software without complex setup steps. For businesses, it simplifies deployment pipelines and reduces the risk of environment-related bugs. Despite its many advantages, Docker is not a silver bullet. It adds a layer of complexity, especially for beginners. Understanding images, containers, volumes, networks, and configuration takes time. Misconfigured containers can lead to security or performance issues. Not every application is a perfect fit for containerization, particularly those that rely heavily on specific hardware or require deep integration with the host system. However, for a vast range of modern applications, Docker offers a practical and powerful solution. Over time, Docker has evolved beyond just a tool into an ecosystem. It includes command line tools, desktop applications, cloud integrations, and APIs. Docker Desktop, for example, provides a user-friendly interface for managing containers on Windows and macOS, making Docker accessible even to those without deep Linux experience. The Docker community has grown tremendously, with extensive documentation, tutorials, and third-party tools. In simple terms, Docker is about control, consistency, and confidence. It gives developers control over their application environments, ensures consistency across development and production, and builds confidence that software will behave the same way wherever it runs. This shift has had a profound impact on how software is built and delivered, enabling faster development cycles, more reliable deployments, and more scalable systems. When you strip away the technical jargon, Docker is really about packaging ideas in a way that makes them easy to share and run. Just as shipping containers revolutionized global trade by standardizing how goods are transported, Docker containers revolutionize software by standardizing how applications are packaged and deployed. This analogy is often used because it captures the essence of what Docker does. It takes something complex and messy and puts it into a standardized box that can be moved, stacked, and handled efficiently. As technology continues to evolve, Docker remains a foundational skill for developers, system administrators, and DevOps engineers. Even as new tools and platforms emerge, the concepts Docker popularized continue to shape modern computing. Understanding what Docker is and why it matters provides valuable insight into how today's software-driven world operates. From small personal projects to massive global services that millions of people rely on every day.